So, well, if you go to our Canvas site, you'll see this fella here. So I'm assuming, again, assumptions are killers. Are you seeing what I'm seeing, which is our Canvas site? Right. Now, yeah. So if we kind of try and stir around some places, because it's maybe a while since you've done, and I've rearranged things a little bit as well. If you click on the Math Office Zoom meeting thing, hopefully it'll change and you can see the picture. And essentially you go down here and you find recorded Zoom meetings. And the one that we're doing today, for instance, will fit in that slot. So far, so good? Right, so if you didn't know that, that's where they're all going now, because they have changed a little bit. And now the other thing I have got is a renaming of something. Basically, I've tried to put everything else in one place apart from the Zoom stuff. So in here, we've got all the various videos. For instance, if you click on this one, here are some videos on line integrals. And some of my videos are here as well. And I kick out of that guy. And if you scroll down to the bottom, it's kind of easy to miss because it doesn't look particularly like there's a lot here, but there's notes and homework examples. So if I click on that one, that's a lot of different stuff we've got saved there over the quarter so far. And here is some notes I've made on the line integral stuff, which is a little bit neater because I did it in Word, but they take forever and a day to do. And then I've got this fella down here. And these are much quicker to do, but definitely not anywhere near as professional looking. What you're looking at here are questions similar to the homework questions from 16.2, so the line integral stuff, and it starts at question 10. And you can see as I go through them, it kind of shows you the various kinds of questions and how I tackled them. Okay, so there's a resource for you. So for instance, when you're on 16.2 and you're thinking, I'm having trouble with question 19 or 18, or let's say it's 17, which is this one here. Here is my worked example of it. And then there's the second takes 2 pages. There's how you do it. So it's a resource. Hopefully you'll take note of that and you'll use it. Okay. I got some things I want to talk to you about, but I would much prefer that I was more useful to you by going over any kind of questions or topics that you have instead of me just picking one that I think you might be interested in. So anybody got a question or a topic they want to start the ball rolling with?
Yeah, kind of just like
Right.
for like the change of variable stuff.
Right.
Just for like some like the more like basic ones I can understand pretty easily. But like when it gets to more like the complex stuff with like the double integrals and stuff like that, could you kind of
Yeah.
just explain that a little more?
Sure. I think the easiest way for me to do that, because you can't really set these questions up just off the top of my head, because if I did, they wouldn't work out. There's those kind of questions like U subs have to work, right? Or change of variable questions have to work. So my excuse for that is I'm going to have to go in and pick maybe
I actually had
oh, have you got one?
yeah, it was
Perfect.
let me make sure I got the right one.
That's what I need.
It was number I like ended up getting these right, but
Yeah.
I think it was yeah, it was number 13 on the 15.9 homework.
Okay, do you have the details to go with it now?
Yeah, so it was the double integral of 7xy. And then it says R is the region in the first quadrant bounded by the lines y equals 2/3 x, y equals 2x, xy equals 2/3, xy equals 2, x equals u divided by v, and y equals v.
I have
Oh,
this one.
That is a lot of stuff, right?
Yeah, that was a lot of information.
A lot of information. Okay. So let's break it into some chunks that are a little bit more manageable. What I need to do with this integral is to convert it essentially into u's and v's. And so it's going to be a new double integral over a new region S. The 7xy is going to become 7 times x, which is u over v, times y, which is v, followed by the Jacobian. Oops. And then you finish with your little du dv thing, right? Are you happy about the setup? Replace the x and the y by u's and v's. Replace the dA, which is essentially dx dy in virtually every question, by the Jacobian du dv. So far, so good. Now, I'm going to kind of take this in chunks. And the first chunk I'm going to get is just the Jacobian bit done. So we have this fella. Darn it in space. Right. Had a brain and be dangerous. Try that again. It's x first. Why my brain wants to go the other way, I do not know. There, finally got it the right way around. Now in this particular question, x is u over v, and we're told that y is just v. So if you do the partial derivative of x with respect to u, you get 1 over v. If you do the partial derivative of u over v, but with respect to v, I don't know if it helps, but you can think of it like that if you like. And it's basically a power rule. You get negative u over v squared. If you differentiate y with respect to u, you get 0. And if you differentiate y with respect to v, you get that. So that's what the Jacobian looks like. Now you do the cross thingy, so major, take away minor. Do you know I'm just going to write down 0 because it really doesn't matter, does it? Because you get 0. And that makes this thing 1 over v. So if I return back to my example that is here, I've got the double integral of some region S. The v's cancel, so I might as well just call that 7u. The Jacobian is 1 over v. And we've got a du dv thing going on. Are you comfortable with where we are right now? Now, we do have some issues, and we're going to deal with them. And the main issue is, how do I describe the new region? That's this region here.
Yeah, that was my
How do I,
problem.
great, that's the problem, right? How do you describe that region using u's and v's? Agreed? Now, the thing is, it's not a one-size-fits-all situation. You have to just take what you've got and run with it. So I'm going to take that chunk. xy is 2/3 and xy is 2. And I'm going to use them. And you might say, well, how am I going to use those? If you take xy, isn't that the same thing as uv times v?
Mm-hmm.
X times y. Agreed? I'm looking at puzzled faces. X times y, uv times v. That simplifies down to u. So do you know xy is the same thing as u? So if xy is 2/3, that means y is 2/3, or u is 2/3. And if xy is 2, y is 2. Do you know I have now got half my integral? I know that u goes from 2/3 to u equals 2. Do you see how I created that relationship? I took the information that was in X's and Y's, I replaced the X's and Y's by what they are in U's and V's, and that generated these two guys. I'm going to have to do the next one in a new piece of paper because it takes more room than that. We have two other fellas to worry about. They are in the first quadrant, so I guess I should make sure that everything I'm dealing with is positive. But essentially what we've got is y is 2/3 x, and then we've got y is 2x. Right, that was the other restrictions. Now, in our story, if you take, oh, I wish I'd give myself more room, I'll do them over here. If you take this fella, if you replace the y with v, and you replace the x with u over v, you get that. If I do a little cross multiply and tidy up stuff, can you trust me that you get 2u equals 3v squared? And that becomes, this is not good planning by me. I don't know how big it is until I start writing, so I don't leave enough room. So here goes. If you rearrange this thing, you get 2/3 u equals v squared. I want to know what v is. I know what u is. I've got limits for u, right? I know that there are two numbers. I'm trying to get v equals. And v equals the square root of that guy. Oh, and by the way, wasn't it in the first quadrant? And when you're in the first quadrant, doesn't that make you positive? So that's why I'm not going to say plus or minus. I'm going to leave it as plus. Now, the other relationship was y equals 2x. Y is v, and x is u over v. So that gets me v squared equals 2u, and that gets me v equals the square root of 2u, again positive. So our double integral becomes u equals, where are we? 2/3 to u equals, it's a number, wasn't it? 2. And v is going to be, hopefully I get this the right way around, that guy to that guy. And the Jacobian part that we had a 7u times a 1 over v, and now I'm going to switch the order because u should come first, or second I should say, and v should come first.
Should that be 2/3 u or root 2u?
This one here?
That's what I was
What,
thinking.
For the, on the,
this thing here is a square root of 2/3 u.
and the other
Well,
one?
this one up here. Ah, darn it. It should be this guy, shouldn't it? I think that's what you're getting at. Yes. Yeah, I just turned to us badly. At this point here, would you just agree it's an ugly double integral from 3 weeks ago? Right. That's what makes these, and I did warn you when you were doing these Jacobians, right? I said, look, these guys are going to kick your butt. Because almost, apart from a few basic ones, they're almost all going to be quite intricate and slightly different each time. And why did I go the way that I went? Because you might say, look, there was tons of information. Where the heck do you even start? That was the key, to start here. Because when you take this and you transfer it into here, do you see that's how I figured out what the new region was? And this allowed me to change the 7xy. And didn't this allow me to get the Jacobian? So basically, if you know what x is equal to and y is equal to in terms of u and v, that's your starting point. That's where everything else branches out from. That's how you get what the new integral is going to be. It won't be 7xy anymore. It'll be stuff with u's and v's. That's the place where you're going to be able to figure out what the new region is. The thing that used to be an xy is now going to turn into UVs based on how do these things interact when you use these on them. Actually, it's kind of unusual from my recollection, at least. I think it's kind of unusual that you actually get variables on these two. I think it's more likely that both pairs are numbers. You know, U goes from 1 to 2 and V goes from 5 to 7. From what I recollect, I think that was the more common version of that question. But that was a sneaky one, wasn't it? Are we good? I'm going to move this. Is there any questions? This is your last chance.
And not on that one.
Not in that one. Okay, that's cool. Right, I'm ready for another question then. You can have a question on something else.
Well, since I missed Wednesday's line integrals thing,
Right.
let me see if I can find a question here.
Line integrals are easy. I can make up line integrals. They're not like Jacobians that you have to be really careful. I can make up a line integral, and virtually all of them are going to work. So do you want me to do one first?
Yeah, can we do number 14?
Sure, that's even better. What is the line integral that you're trying to do? If you've got that handy, otherwise I have to go in and look for it as well, and that takes time.
I've got mine up here.
Okay.
It's the integral over the region C of f dot dr, where C is given by the function r of t, and f of xy equals xy I plus 9y squared j, then r of t equals 14t to the 4th I plus t to the 6th j.
Now you may have noticed as he was doing those questions, I turned them into this notation. That is purely cosmetic. You know, I, J, K notation and component form, you know, the little funny brackets. That's a bracket, by the way. It's not a less than or greater than. They are totally equivalent. Just for my brain, that works better. Now, there is a formula for doing, there should be a t value. It's normally 0 to 1, but
yeah, it's bounded to 0 to 1.
right. But it could be 10 to 20. That's just number crunching, so we're not too worried about that. Right. This is one of the many flavors of line integrals. This particular one gets turned into that guy. So what you are going to do is you differentiate the curve with respect to t. You do a dot product with the vector function, f of xy, with everything turned into t's. And when you do a dot product, you just end up with a scalar. So that's going to end up as a single integral from t equals 0 to t equals 1. So you don't need to worry about Jacobians, what's the new limits. Whatever t starts to whatever t finishes, typically. Now let's take the pieces in turn. So this guy is 14t squared t to the 6. His derivative is 28t 6t to the 5. You all comfortable with that? Basically calc 3, isn't it? Derivative of this guy, calc, calc 3. Remember doing space curves and differentiating space curves. R dashed of t, right? Differentiating them. That's what's going on there. Is my writing's too small? Because some of you look like you're having a hard time seeing it. Is it the quality of the screen?
I think it's just that it looked like the vector RT was 14t to the 4th, is how it looks up there.
Oh, then that's probably correct, in which case that can now turn into a cube. Is that it?
Yeah, and 28 has to go on a spiritual journey for a new number.
Oh, God, what spiritual journey is 28 going to go on to? 16 to the 5 is good.
Yeah.
Right, we'll use those. You're just going to get an ugly number when we're finished anyway. So it's integral from 0 to 1. Now you might think, how do you do this fella? This fella is not hard. You just replace the x with this guy and you replace the y with that guy. So the first term is going to be x times y, comma. The 9y squared is going to be 9 t to the 6 squared. dot product with this ugly fella, 28t cubed, 6t to the 5, and then do a dt. Now you can write it down in IGI notation. I typically don't, as you know, I make enough mistakes. If I'm not very careful, do you know my i's and j's almost look the same, and half the time I write the next guy with the wrong guy. But here it goes. It's integral from 0 to 1. That guy is 14t to the 10 times this guy. 14 times 28. That's going to be a fun one. Let's see. How did that turn into 48, 28?
No, no, because the f vector should be xy 9y squared.
Right, and xy, I'm talking about this guy here. This guy should be 56t cubed. So that's where the spiritual thing went. I should have just left it with my squared. It would have been better. Okay, this guy times this guy. You're getting 14t to the 10 multiplied by 56t cubed added to 9t to the 12 times 6t to the 5 dt. And that's going to be the integral from 0 to 1. And now I'm going crazy with a calculator. If you multiply 14 and 56 together, you get 784. And t to the 21. And if you multiply these together, you get 54 t to the 17 dt.
Wait,
Question?
and then we integrate that once more.
Yeah, it's just Calc 2 now. Yeah, and you're going to get 57 329ths or some weird answer, and you call it good. Line integrals end up being single integrals with respect to t, which means they all end up being a Calc 2 integral when you're finished. So you're going to spend a lot of time doing power rules, now and again U subs, and even rarer integration by parts. But you're still just going to end up with an ugly integral with respect to t, an ugly single integral with respect to t, that you use the usual techniques that you do on in the Calc 2 world, right, way back in the day.
So what happened with the f vector?
The f vector, he get turned into that guy. So the xy became this, and the 9y squared became that. And all I was doing is substitution. I want you to think of that as your x and that as your y.
Okay, I see it now.
And so it was substitution. And that's kind of what you do. You get a lot of substitutions as well.
All right.
So I
Cool.
can't really see after that F that you circled, what does that next one say?
This
I
one
can't-
here,
It's, yeah, but when you wrote it down in the integral, it's really tiny.
oh God. This,
Um,
are we talking here?
No,
She's pointing just to the right of that one you just circled, where it's got like the scratched out bit on the far right.
yeah,
This thing here?
Yeah, there.
That guy, after about 3 attempts, became 56t cubed, comma, 6t to the 5, with a dt at the end. So that mess there is 56t cubed and 6t to the 5 dt.
oh, okay.
It was just really tiny because I run out of room.
How did 14 t to the 4 t to the 6 become 14 t to the 18?
How did this become that? Because I multiplied that guy with that guy, and that is our x, and this is our y. And so I multiplied x, which is 14t to the 4. Oh, how did it become?
It should be a 10, shouldn't it?
I
Should
think it's
be
a
darn it.
13. I think it's a 13 from the dot product.
Yeah. Yeah, there's another guy over here that's true, but this here should have been a 10. Good. Okay. I just basically screwed that question up. It is nowhere near as hard as that is. I'm doing another one, only this time I'm taking twice as long and will only make half as many mistakes. Because the number of mistakes is inversely proportional to how quickly I try and do them. And I can't do questions quickly. So I'm going to do...
It'll take about the same amount of time as the previous one.
Right, probably. So let's pretend we had another question. Very similar to the one I've got. This time I'm just going to write down the things a little bit slower and try and give myself more room. So imagine this is the curve, and we're going to do the curve from 0 to 1. And we're going to have a vector function. And this vector function is x plus y and xy, just for argument's sake, right? And we're being asked to calculate this line integral. So it's going to be the line integral of this guy, that guy. That's going to be the integral from 0 to 1 because of this. It's going to be the vector f dot product with the derivative of r dt. So that's the standard formula for this type of line integral. So any line integral that has an f dot dr, you're going to do this to. Now in this question, the vector f, which is this fella, and I'm not even going to change him yet, I'm leaving him just for a little while longer in his original form, dot the derivative of r. If you take 14t squared and you differentiate it, you get 28t, comma. If you take 5t cubed and you differentiate it, you get 15t squared, and you finish with the dt. Are you happy about how we got from here to here? Can you follow the steps of what I've done?
Yeah, now I can follow.
Now I'm going to have to move over here because I know how much room based on the last question I needed. So I'm going to do the integral from 0 to 1. Instead of x plus y, that's going to be my x and that's going to be my y. So I'm going to have 14t squared plus 5t cubed. That's what x plus y looks like now. 14t squared plus 5t cubed, comma. xy is going to be 14t squared multiplied by 5t cubed. That's what xy is going to look like. Dot product with this stuff. 28t, 15t squared dt. Are we comfortable about where the bits that I've now got are, right? So be prepared for me screwing up now, because we got this far, I'm bound to screw up somewhere, right? Actually, I'm not, because I've decided to take things really slowly, and I'm not going to do anything major at all. I'm just going to multiply these two together and get 70t to the 5. Nobody would probably need that line, but based on my last question, I'm just playing safe. Are you happy about where the 70t to the 5 came from?
Yeah, looks good.
You probably didn't need that line, as I said. Right, now I'm biting the bullet. Dot product, this guy times this guy. So 14t squared plus 5t cubed multiplied by 28t. Remember the dot product, x times x plus y coordinate times y. So plus y coordinate, or y component, I guess, times the other guy's y component, dt. We better? Comfortable? No screws up so far detected? That's going to be the integral from 0 to 1. If you multiply through by 28, no chances of me doing that in my head. So 28 times 14 you get 392 t cubed. That guy times that guy is 140 t to the 4. This guy times this guy is 70 times 15, which is 1050 t to the 7 dt. And I'm dotting there. But can you see that would just be a really ugly power rule, and plug in 0, plug in 1, and get some ridiculously ugly fraction. But more interested, that is the process for how you do that particular kind of line integral. Any questions about that one? It's much easier to do when you don't rush and you don't screw up all over the place, right? It's really just, it's a pretty turn the handle and out pops the answer kind of question, which you don't get very many of these, so you enjoy them when you do get them.
I had a quick question about just like line integrals in general.
Sure.
So I was noticing for some of them, so for line integrals where like the original integral is with respect to like s with like respect to like the length of the curve.
Yes.
That's when you would use like the square root of the derivative of x
Yes.
derivative of y. But if it was for some of them where it's like just derivative of x derivative of y, you wouldn't use the.
Yes.
Okay, I just wanted to make sure.
Right. There is, in this section, there are different kinds of line integrals. It's not one question. It's different versions of different kinds of line integrals. I don't know why that popped up, because it shouldn't have. Right. So let me give you a kind of the different flavors of them. I can certainly write down some examples quite quickly off the top of my head. I'm not guaranteeing I'll do them, but we can certainly do one if you want me to. One of the kinds of questions you get would be a line integral over some curve C, and it might be xy ds, right? For example. Second kind of line integral that you might get, they look like that. In fact, that's the one we just did, right? One that's in that family.
Mhm.
There's another kind of line integral that you get that looks like this. There's another kind of line integral that looks like that. So these are all examples of different kinds of line integrals. What ties them together? Single integral over some curved region, some line. But you might integrate a function with respect to the arc length, which is what that represents. You might be doing it in this case. Do you know this one here is almost always used when you're trying to find the work done? So if a object moves through a force field F and the path that it takes is C, then the work done is given by this line integral. This here is a line integral in respect to y. And if you want to visualize what that looks like, can you imagine a surface z equals xy? And then on that, you drew a curve, and it kind of like somebody walked around the mountain, right, in a particular pathway. And then you looked at it from the orientation of y. That's what that line integral would look like. Now, if you've got a good visual, you can imagine that, and if you can't, don't worry about it, because it doesn't stop you from doing the questions, but that's what it is. And this weird thing here is actually just a notational simplification. It really just means two of these guys. So you basically do two separate line integrals. Or you can combine them. You'll see in the math that you can. Right. Now, when you do this fella up here, the x's and the y's turn into some function of t's, don't they? Sorry, not this time. This is the one where you do the dx by dt squared plus, see, I'm making a mess. Try it again. Slow down. You would do your x converted into a function of t, your y converted into a function t, and then the square root, you know, the one that looks like this. Right, that's what that one looks like. This one is the one we just did. In this one and in this one, there isn't really so much a formula, but a way to do it. Convert everything into t's. And then almost every single, not almost, every single one of these questions, there's a c attached to it, right? Now, the best way to be told c is to be given the parametric equation of it. You can either get it written like this, which is kind of convenient for this one, or you can be given the same information like that. This and that are equivalent, right? Those are the easiest ones to deal with because everything is pretty much ready to use. Because when you do these questions, most of the time, they make sure t is 0 to 1. So you know your integral is going to go 0 to 1. And then all you do is you make everybody else turn into t's. So I'm now going to do a slow version of the question we just looked at. Let's suppose you want to do a line integral of this form. X squared dy plus y dx. Right, I need a curve. Don't make my life horrible, because if you do, it's just going to reflect on everybody. Give me a reasonable parametric curve for this line integral to be integrated over. So tell me x equals this and y equals that, just to start the ball rolling.
X equals t cubed.
Yeah, nothing wrong with that. Y,
e to the x.
or we'll call it
e
e to the t. Yeah, perfect. Right, those I can handle, right? We don't want to make them ridiculous.
Jeez, man, I don't want to keep shooting people.
Right. Your cat causing you trouble?
Yes.
So I say. Okay, so there is some preparation to be done here. Oh, and can we just say 0 to 1, right? Because everybody's 0 to 1, right? Some preparation to do here. I know that x is t cubed. If I differentiate x with respect to t, I now get 3t squared. That means that the differential dx is equal to 3t squared dt. Does that look familiar to you, that process?
That's u sub.
It's essentially a u sub kind of question, isn't it? It's connected to, it's not perfectly the same, but it's pretty close. Now there's e to the t. So if you differentiate that guy with respect to t, you get e to the t. And what you now have is e to the t dt. What we've found is I can now replace the dx with this guy. See, dx is now in terms of t. And you see I can now take this differential dy and I can replace him again with respect to t. You see where this is going? Everything here is going to turn into t's, either limits or the thing itself. So the integral is going to go from 0 to 1. X squared is going to become t cubed squared. Dy is going to become e to the t dt.
Uh-huh.
Now, I'm going to separate them into two integrals. So imagine there's another one there, because that's what you're allowed to do. 0 to 1, y dx, y becomes e to the t, and dx becomes 3t squared dt. And this now becomes the integral from 0 to 1, t to the 6 et, plus the integral from 0 to 1, 3t squared e to the t. And at this point, it's time for dot, dot, dots. Would you agree that both those single integrals are just really ugly, repeated integration by parts? Right, I can't do a U-sub on it, but yeah, the technique's there, right? You could, you know, half an hour, 20 minutes, whatever it takes you to do multiple ones. That guy will eventually integrate, won't it? And you'll be done. So if you get a question that's like this, or if it was only a single one, you know, like x, y, dx, that's a line integral. So it was only, say, that piece. You see, your answer would look almost the same working, but you'd only have the left-hand side piece. Right, so if you were doing x squared dy, you would end up with t to the 6, e to the t dt, and you'd get it the usual calc two-way.
And that's only about 20 minutes of working.
Yeah, I mean, there are a lot of questions. Well, I don't think, I've went over the last bunch of questions on this, and none of them were 20 minutes. I think all the numbers came out relatively nice. So, yeah, that's what you get for randomly picking functions, right? Now, I want to show you a problem that we haven't coped with, and we do need to. Let's suppose I want to find a simple line integral, so there is such a thing. It's just going to be x dy over some curve C. So you couldn't get much simpler as line integrals go. So how am I going to make the question difficult? The thing is made up of the line joining 0, 0 to 1, 2, and then from 1, 2 to 4, 5. Now, if you imagine what that looks like visually, you're going from 0, 0 to 1, 2, and then 1, 2 to 4, 5. And I'll call this piece C1 and I'll call this piece C2. What this question has been created for is to show you that you don't always get the curve C given to you handed on a plate. They don't say C is x equals t and y equals e to the t, right? They don't say r of t is t squared comma t cubed. Those guys, you're given the answer, you are good to go. We have to create our own. Now, I'm going to have to create it into two pieces. So the math says that what you do is you break it into two separate line integrals. One of them for the line C1 and a different integral for the line C2, and then you just add the two pieces together. So far, so good? Right, let's look at C1. It starts at the origin and it finishes at the point 1, 2. And would you agree that that is the line y equals 2x? Without me getting into the details of y. Are you comfortable about the line from 0, 0 to 1, 2 is y equals 2x? Agreed? Now, I don't want y equals 2x. I want parametric version of y equals 2x. Agreed? I need x equals a function of t, y equals a function of t, because everything turns into t's, right? Remember, that's the goal. Everything turns into t's. So how about this? Make x equals t and y make that equal to 2t. Won't that do the same job? It's not hard to turn any equation of the form y equals into a parametric. Just make x equals t and y will be the same formula, but x is replaced by t's. So that's how you do it. Now, the only other thing I need to do, I'll tell you that, is I do need to know for that line where to start and where to finish. T equals 0 is where I start. What value of t will I finish on that integral?
1.
Correct? Why?
Because that's where x finishes.
Yeah. You see x finishes at 1, so it goes from 0 to 1. So t goes from 0 to 1. That means this integral here is the integral from 0 to 1. This integral here isn't the x equal to t. And in this integral here, I'm going to just do it in my head. If y equals 2t, won't dy by dt be 2? And so dy will be 2 dt. Are you happy about how I got the dy? Or do you need me to write this down? You want to see it? Or are you comfortable with me just telling you what it is?
Can you write it, please?
Sure.
Thank you.
So y equals 2t. If you differentiate it with respect to t, you get 2. If you do the little crossover deal, there you go. So this integral here becomes the integral from 0 to 1 of 2t dt. And now you move on and you do the second guy. Now I'm going to be starting here and finishing here, right? Starting at 1, I guess, and finishing at 4, right? In the same way that I did this question, what I'm now going to have to do is find the equation of that line and then turn it into parametric form, and then I can use it. So I'm going to have to put a bubble around this guy, and I guess I'll squeeze it in here. If you take this point and you join it to that point, do you know how to get the equation of a line that does that? Find the slope and y minus y1 equals m brackets x minus x1 and all that good stuff, right?
Yeah.
And I'm telling you what the answer is, and you can go and double check that I didn't screw up later. But going from here to here and here to here, it's an x. So I know it's got that in it. And then it's a plus 1. So it's y equals x plus 1. Because I'm telling you it is. But you can check it. Which means in parametric form, won't it be x equals t and y equals t plus 1 then? Right. And where will the t start and where will the t finish for this second line, this line that we're calling C2?
1 to 4.
And are we all happy about starts at 1 and finishes at 4, and that's where the 1 and the 4 came from? Right. So our integral is now going to be from 1 to 4. The x is going to get replaced by t again. The dy, okay, this I don't have room for, but would you agree that if I do y equals t plus 1 and I do the same kind of thing as I get here, would you agree that dy ends up being dt? Right, 1 times the thing. Right, so I can do that guy. So we are now looking at that integral. And now I'll just do dot, dot, dot plus dot, dot, dot equals answer. Now I tried to keep that question relatively simple by making this x, but can you imagine this could be x cubed y dy plus sine x dx, right? It could be really ugly, right? Do you know the only difference in that really ugly version would be there'd be a lot more pieces, the x's and y's that would be turned into t's and 2t's and whatever x and y end up becoming. And so you probably just end up with a really massive polynomial that you can still integrate, but just big. Right, we're really getting time up. So any last question that we may have time to zoom through, or a concept that you're unsure about?
Speaking of that kind of same thing where you have to find the t on your own, number 16 had a weird one.
Okay, let's see if we can just do the t on its own part, right? How did they describe the curve in, you said question 16?
Yeah, which was about evaluate the line integral where c is the given curve, integral of c x e to the y dx, and
x e to the y, dx, okay.
Yeah. And c is the arc of the curve x equals e to the y from point 1, 0 to point e to e cubed 3.
Right, that guy.
Yeah.
Oh, good news. It's not as hard as you think. It's just unusual. if you can tell me the equation of the curve, right? Y equals x cubed, y equals 2x plus 1, then I always make x equals t and y what's left. But you can switch it. You can make y equals t, and that makes x equals e to the t, and that does the job. You see what I did there?
I see what you did there.
This is the curve, x equals e to the t. I just said, okay, if I make y equals t, it's dead easy to get x, isn't it? It's much more difficult if I made x equals t. I'd get some weird log stuff I don't want to do. Right. I still need to know start and finish number, don't I?
I think this one just goes from 0 to 3 then.
And you're correct. Tell us why, because not everyone might say that.
Because if the t equals y, then you just take the y coordinates of the points given.
Yes. Y starts at 0, y starts at 3. The mistake you might have made there, because almost every question x equals t, would be you'd say from 1 to e cubed. Can you see that that would screw up your integral? Everything else might be right, but 1 to e cubed is not the right level for x's, right? T goes from 0 to 3.
Okay, so for something like this, if you have one variable equal to equation with a different variable, the equation of the different variable has a different variable equal to t, and then the x is equal to whatever the equation of that was.
Imagine that. Nobody would give you that, but imagine they gave you that. If you want to make that parametric, make y equal t and x equals that guy.
Yeah.
The more likely equation is something that looks like that.
Yeah.
In which case, you make x equals t, and y gets the other guy.
Yep.
Right, so one of them's t, and the other is whatever, right? And you choose the one that is easiest to deal with, given the information in front of you. So, I mean, if you tell me a y equals, I'm going to go this road, right? If you tell me an x equals, I'm going to go that road, right? To me, there's really one obvious choice that you should go because it's easier to deal with. Do you know if we rearranged this one here? Where is it? Third time lucky. If I took the log of both sides, I would get that. Agreed? Now, I could have made x equals t and y equals log t, and that would have been a valid choice, except for one thing. My experience has told me that logs are dangerous things to stick anywhere inside an integral.
Yep.
Just computational wise, right? They tend to cause havoc. And so I would have avoided it for that reason. So I'm not saying you couldn't have just made everybody a y equals and, you know, have a single rule for every situation, but sometimes it's just better to go with the flow. If they've written it in this particular format, it's probably because they want you to go that particular road.
And in the other case, you would go from 1 to e cubed for the t values.
Yeah, you would. Yes, your choices would have moved because of that as well.
Makes sense.
Your t values would have changed because you're now using x equals t, so it's what the x coordinates are doing rather than what the y coordinates are doing. I'm assuming that is it, right? You know this Sunday you've got your test. Trust me, you will. It's got fewer questions, but they are longer. You're kind of getting used to that. We have fewer questions, but they're harder to do. Make sure that you do as much working as possible. I can't tell you how often that has saved some of your butts. If I only used the score that they had in the software, it is cruel. The software says the thing's worth 5 points. You make one tiny mistake, the answer's not right, you're getting a 0 out of 5 because that's the way it does. And then I look at your working and I say, darn it, that was silly, they got 4 out of 5, and you've made a lot of points. So you can't let that slide. You need to get your Canvas upload when you're finished. So don't start at 11 and think you can do it in an hour and send stuff. You got to start like 9 o'clock to give yourself 2.5 hours to do it, and a half hour to, send the work into me so that I can improve your grade by
And
giving you partial credit.
from the experience side of things, don't try to do your homework on Sunday either.
A good piece of advice, Kawika. I hope you're taking your own advice. If not now, then definitely in the future.
I'm working on it.
Okay, you're working on it, right? That's it. It's Monday is a holiday for me. It's a holiday for you. So I am not taking Zoom meetings. I am going to desperately try and not look at emails. So if you send me an email on Monday, I won't reply until I look at it on Tuesday morning. I will be on and off about Saturday and Sunday, although that's technically not my the days I'm meant to be working, but I'll be around. So if you shoot me an email, you might have to wait a couple hours because it may be a couple hours between me looking at one and going back and looking again. But I will try and get back to you because the test is coming up and I may be able to fix some things before that.
Do we still have a quiz?
Not for let's check this one. I'm not going to say something that's not true. I do not believe there is a quiz. I'm just checking this out as I speak. Darn, it takes for ages to do this, doesn't it? Just logging in, almost there. Zoom it to the bottom, see if we do have a quiz. Nope, there is no quiz. There is a 16.1 homework, 16.2 homework, and the test.
Thank you.
You want practice, you're going to have to look back at your work from 16.1, well, from 15.7 to 16.2 and do that. Yeah. I think the reason I chose not to do it is that your work was already, if you're doing this correctly, you're already working a lot to get just the homework questions done. And I don't want to give you a quiz on top of that, like just be overworking you. So I'm good to go. Have a nice day, everybody. And I shall see you on Tuesday for a meeting, because that's when I'll probably do the Zoom meeting for us. And goodbye.
Yep, that actually works out perfectly for me.
All right, thank you.
You're welcome.
Thank you.
Bye, guys.
Bye.